Hello, in this lecture we will find the radius of the small circle. In the drawing we have a square ABCD. We know that all the sides of this square are equal to 8 units, and inside the square we have two circles. The radius of the big circle equals to 2r, and the radius of this small circle equals to r, and we want to find out the radius, the value of r, or the size of the radius of this small circle. So first of all, I will present to you two new rules. The first rule is number 1. States that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. I will repeat again on rule number 1. Rule number 1 states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if you have this circle and suppose that the center of this circle is at this point, and this point is defined as point O, and we have tangent to this circle AB is tangent to this circle at this point. We define this point, the touching point between the tangent to this circle, as point M. And if we have here the radius of this circle, this is the radius of this circle, I will define it as r. So if the radius of this circle, that is to say r, is drawn to the point of tangency, that is to say point M, as we can see in this drawing, then the tangent AB is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle is also equals to 90 degrees. So whenever you have a radius of a circle that is drawn to the point of tangency, like in this drawing, then the tangent AB will be perpendicular to this radius, that is to say this angle is 90 degrees and this angle is 90 degrees. Okay, so this is actually rule number 1. A tangent to a circle is perpendicular to the radius drawn to its tangency, and we also have rule number two. Rule number two states that if from one external point two tangents are drawn to a circle, then they have equal lengths. Equal lengths. They have equal lengths. I will read rule number two again. Rule number two states that if from one external point two tangents are drawn to a circle, then they have equal lengths. So what is the meaning of rule number two? The meaning of rule number two is that if you have external point to this circle, let's define this point as point P. Point P is an external point to this circle because of the fact that point P is neither inside the circle nor on the circle. For that reason, point P is an external point in relation to this circle, and if from point P we will draw two tangents to this circle, this is the first tangent to this circle. We will define the touching point between this tangent to the circle as point A, and we will draw from point P the second tangent from another tangent to this circle. This is the second tangent to this circle, and we will define the touching point between this tangent to the circle as point B. So according to rule number two, if we draw from external point two tangents to a circle, like in this drawing, then the lengths of those two circles will be equal, the length of those two tangents will be equal to each other. That is to say, PA will be equal to PB. Okay, so according to rule number two, whenever you have a circle and external point, and from one external point to this circle, like in this drawing, you draw two tangents to this circle, then the length of those two tangents will be equal to each other. That is to say, PA equals to PB. Okay? So that is rule number two again. I will read it again. If from an external point two tangents are drawn to a circle, then the lengths, or they have equal length, so the length of two circles that are drawn from one external point to the circle, like in this drawing, we drew two tangents from external point P to this circle. The length of those two the length of those two tangents are equal to each other. That is to say, PA equals to PB. Okay, so that is rule number 2. So in the next step, we will define the center of this small circle as point P, and we will define the center of this big circle as point Q, and then we will join points A and P together by a straight line. From point P, we will draw, first of all, we will define the touching point between tangent AB to the small circle as point M, and then we will join together points P and M by a straight line. Actually, PM is the radius of the small circle because of the fact that it starts from the center of the small circle and ends at point M. That is a point on the circle itself. Therefore, it is defined as the radius of the circle. We will define it as R. Okay, R is the radius of this small circle. And according to rule number 1, when you have radius that is drawn to the point of tangency, like in this drawing, like here, you have this radius that is drawn to the point of tangency, that is to say to point M, then the tangent AB will be perpendicular to this radius. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the next step, we will define this point as point E, and we will define the touching point between tangent AE and the circle and the small circle as point E, and then we will join together points P and E by a straight line. Actually, line segment PE is the radius of this circle. We will define it as R, the radius of this small circle, because of the fact that line segment PE starts from the center of the small circle and ends at point E, that is a point on the circle itself. Therefore, PE is the radius of this small circle, and according to rule number 1, this radius PE is drawn to the point of tangency, that is to say to point E, that is the point of tangency. Therefore, the tangent AE is perpendicular to the radius. That is to say, this angle is a right angle, it equals to 90 degrees, and this angle is also a right angle that equals to 90 degrees. Okay. Here we will define this point as point F because we have already point E, so this point will be defined as point F. And in the next step, we will prove that those two right triangles can go into each other. So we will focus on triangles, the right triangle, triangle AMP, and the right triangle, triangle AEP. We'll repeat again. We will prove that the right triangle AMP is congruent to the right triangle AEP. Okay. First of all, AEM, side AM equals to side AE. AM equals to AE according to rule number 2. AM equals to AE according to rule number 2. We have why AM equals to AE because we have here point A that is external point to this small circle, and from point A we have two tangents to this small circle, tangent AM and tangent AE. And according to rule number 2, when you draw two from an external point, you draw two tangents to a circle, then the lengths of those two tangents will be equal to each other. That is to say, AM equals to AE. Okay? So AM equals to AE according to rule number 2. And we also know that EP equals to PM equals to the radius of this small circle, or PE equals to PM equals to the radius of this small circle. Again, PE equals to PM equals to the radius of the small circle, R. And we also have here a side that is a common side. PA is a common side, it belongs to both triangles. So we write that PA equals to PA as a common side that belongs to both triangles. So PA equals to PA is a common side that belongs to both triangles. So we actually proved that all three sides of the right triangle, triangle AMP, are correspondingly equal to the three sides of the right triangle, triangle AEP. Therefore, we proved that the right triangle AMP is congruent to the right triangle AEP. So I'll write it down. We actually proved that the right triangle AMP is congruent. This is the sign of congruent to the right triangle AEP according to side rule. So what is side rule? Side rule is that if you prove that three sides of one triangle are corresponding equal to three sides of another triangle, then you actually proved that those two triangles can go into each other according to side rule. Okay, and we prove that three sides of this right triangle are corresponding equal to three sides of this right triangle. Therefore, we prove that those two right triangles can go into each other according to side also. So, from the fact that those two triangles can go into each other, we will conclude that this angle equals to this angle, or angle MAP in triangle APM is equal to angle PAE in triangle EPA, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding angles will be equal to each other. So we write down that angle MAP, this angle MAP, is equal to angle PAE. Again, according to the rule, corresponding angles in congruent triangles are equal to each other. And if we define angle MAP, this angle is alpha, then angle PAE will be also equal to alpha because of the fact that those two angles are equal to each other. So we actually found out that angle MAP is equal to angle PAE, and it equals to alpha according to our definition. Okay? So, in the next step, we will join together points A and Q by a straight line. And we will define the touching point between tangent AE to the big circle. This point is point L, and then we will join together points Q and L by a straight line. Actually, QL is the radius of the big circle because of the fact that line segment QL starts from the center of the big circle, that is to say from point Q, and ends at point L, that is a point on the circle itself. Therefore, QL is the radius of the big circle, that is to say it equals to 2R. And actually, according to rule number 1, we have the radius of this big circle that is drawn to the point of tangency, that is to say to point L. Therefore, the tangent AF is perpendicular to this radius, that is to say this angle is a right angle, it equals to 90 degrees, and this angle is also a right angle that equals to 90 degrees. And we also have this radius. First of all, we define the touching point between tangent AD to the big circle as point N, and according to rule number 1, this radius is drawn to the point of tangency, that is to say to point N. Therefore, the tangent DA is perpendicular to this radius, that is to say this angle is a right angle, it equals to 90 degrees, and this angle also is a right angle that equals to 90 degrees. So in the next step, we will prove that those two right triangles can go into each other. Okay, so actually we will prove that the right triangle AQL, this right triangle, is congruent to the right triangle NQL. I will repeat again. We will prove that the right triangle AQL is congruent to the right triangle NQL. So first of all, AL is equal to AZ. AL equals to AZ according to rule number 2. Again, AL equals to AZ according to rule number 2, because of the fact that from the external point A, we have two tangents to this big circle, tangent AL and tangent AZ. And according to rule number 2, whenever you draw from an external point of a circle two tangents to a circle, then the lengths of those two tangents are equal to each other. That is to say, AL equals to AZ according to rule number 2. And we also know that QL, that is the radius of the big circle, equals to QZ, that is also the radius of the big circle. That is to say, QL equals to QZ equals to the radius of the big circle. QL equals to QZ equals to the radius of the big circle. And also we have here a common side. QA is a common side, it belongs to both triangles, so we will write down that QA equals to QA is a common side that belongs to both triangles. So QA equals to QA is a common side, so we actually proved that all three sides of the right triangle AQL, 1, 2, 3, are correspondingly equal to all the three sides of the right triangle NQL. Therefore, we actually proved that the right triangle AQL is congruent to the right triangle NQL according to side rule. So I will write it down. We actually proved that the right triangle AQL is congruent. I will repeat again that this is the sign of congruent to the right triangle NQL according to side rule. Okay. Okay. And from the fact that those two right triangles congruent to each other, we will conclude that this angle, actually angle LAQ, is equal to this angle QAZ or ZAQ, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles congruent to each other, therefore those two corresponding angles will be equal to each other. So I write it down. Angle LAQ is equal to angle ZAQ angle LAQ equals to angle ZAQ, and if we define this angle as beta, then this angle will be also equal to beta because of the fact that those two angles are equal to each other. Okay, so we actually found out that angle LAQ is equal to angle ZAQ, and both angles are equal to beta according to our definition. Okay. So actually we define the touching point between tangent BC to this small circle as point S, and we have this radius that is drawn to the point of tangency. That is to say, it is drawn to point S, that is the point of tangency. Therefore, the tangent BC is perpendicular to this radius. That is to say, this angle is a right angle, it equals to 90 degrees, and this angle is also a right angle that equals to 90 degrees. And we also know that all four angles of a square are right angles. And angle ABC, this angle, is one of the square's angles. Therefore, it is a right angle that equals to 90 degrees. Okay? So, in the next step, we will focus on the quadrilateral PSMB, this small quadrilateral. So we'll focus on quadrilateral PSMB. In quadrilateral PSMB, this quadrilateral, we have three right angles, 1, 2, and 3. And the sum of three right angles is 270 degrees, because 90 times 3 is 270 degrees. And we have a rule that states that the sum of the angles in any quadrilateral equals to 360 degrees. So the sum of the four angles in quadrilateral PSMB equals to 360 degrees. So if we define the fourth angle as angle Z, then the sum of those two angles, that is 270 degrees plus the size of the fourth angle, must be equal to 360 degrees. I will repeat again, we will have this equality that the sum of three angles of quadrilateral PSMB plus the size of the fourth angle, angle Z, must be equal to 360 degrees according to the rule that I mentioned. So here we will subtract from this equality 270 degrees, and we will get that angle Z equals to 360 degrees minus 270 degrees is 90 degrees. So we found out that the size of angle Z equals to 90 degrees. Angle Z equals to 90 degrees. So this angle is a right angle that equals to 90 degrees. So as you can see from the drawing, quadrilateral PSMB has four right angles. And any quadrilateral that has four right angles, it is at least rectangle. So I will write it down. Quadrilateral PSMB is at least a rectangle. Is at least rectangle, if not square. Okay, quadrilateral PSMB is at least rectangle, because any quadrilateral that has four right angles is at least rectangle, is not, if not square, it is at least rectangle. And we have a rule that states that any quadrilateral, so we know that quadrilateral PSMB has four right angles, and therefore it is at least a rectangle. So, and we have the rule that states that the opposite sides of any rectangle are equal to each other. That is to say, PS equals to MB. According to the rule that I mentioned, that the opposite sides of a rectangle are equal to each other, PS equals to MB. Even if quadrilateral PSMB is not a rectangle but a square, then let alone that the opposite sides of a square are also equal to each other because all the sides of a square are equal to each other. So it doesn't matter at all if quadrilateral PSMB is a rectangle or square, because anyway the opposite sides of a rectangle and the opposite sides of a square are equal to each other. That is to say, PS equals to MB. Okay, because of the fact that the opposite sides of a rectangle or a square are equal to each other, that is, it means that PS equals to MB. So if PS equals to MB, we know that PS is the radius of the small circle, that is to say it equals to R. So PS is the radius of the small circle that equals to R. So from this equality we will derive that MB also equals to R. MB also equals to R. So MB also equals to R. So, and we have also the opposite sides of this rectangle or square. PM is equal to the opposite side SB. PM equals to SB. According to the rule that the opposite sides of a rectangle or a square are equal to each other, PM equals to SB. But we know that PM is the radius of the small circle, it equals to R. So we know that PM equals to R, so from this equality we will derive that SB also equals to R, SB also equals to R, the radius of the small circle, SB equals to R. Okay, so because of the fact that all the sides of quadrilateral PSMB are equal to each other and it has 4 right angles, actually quadrilateral PSMB is a square. Okay, and so we know that MB equals to R and AB equals to 8 units according to what is given us in the question. AB equals to 8 units. So here we can draw this line that is actually the length of AB, that is actually equals to 8 units, and MB equals to R. So what is the size of AM? AM equals to AB minus MB again. AM equals to AB minus MB. Okay, so I will write it down. Line segment AM, this line segment equals to AB minus MB. From the drawing you can see that AM equals to AB minus MB, but we know that AB equals to 8 units and MB equals to R, so actually AM equals to 8 minus R. AM equals, this line segment AM equals to 8 minus R, and we will actually repeat on the same process on the other side of the square, in the upper side of the square. First of all, we will define the touching point between side DC, the tangent DC to the big circle, this point H, and then we will join together points Q and H by a straight line. So actually QH is the radius of the big circle because of the fact that line segment QH, starts from the center of this of the big circle, that is this point, and ends at point H, that is a point on the circle itself. Therefore, that is exactly the definition of a radius. So therefore QH is defined as the radius of the big circle, that is to say it equals to 2r. Okay, and again we have rule number 1. We have this radius that is drawn to the point of tangency, that is to say to point H. Therefore, the tangent DC is perpendicular to this radius, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay, and we also know that all the angles of a square are right angles, therefore this angle is a right angle that equals to 90 degrees. So we will focus on quadrilateral DH, DH and Q. We will focus on quadrilateral DH and Q. So in quadrilateral DH and Q, we have 3 right angles, 1, 2, and 3, and the sum of 3 right angles is 270 degrees, and we will define this angle as angle Z. So we know that the sum of all angles, all 4 angles of a quadrilateral is equal to 360 degrees according to the rule that I mentioned. The sum of the angles in quadrilateral D, H and Q equals to 360 degrees. Therefore, the sum of 3 angles, that is 270 degrees, plus the size of the 4th angle must be equal in total to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we will subtract from this equality 270 degrees and we will get that angle Z equals to 360 degrees minus 270 degrees is 90 degrees. So we actually found out that angle Z is a right angle, it equals to 90 degrees. Okay, so actually quadrilateral DHZN has 4 right angles, and as I already mentioned a couple minutes ago, that any quadrilateral that has 4 right angles must be at least a rectangle. If not a square, it must be a rectangle. So I'll write it down that quadrilateral DH and Q must be at least a rectangle. And we know that the opposite sides of a rectangle are equal to each other, that is to say DH equals to NQ, DH equals to NQ, but we know that NQ equals to 2R. Okay, NQ equals to 2R. So from this equality we will conclude that DH also equals to 2R. So I write it down that the edge equals to 2r, and we also know that the opposite sides of a rectangle the edge and q are equal to each other. That is to say, this dn equals to hq, dn equals to hq. According to the rule that the opposite sides in the rectangle are equal to each other, the edge equals to dn equals to hq. But we know that hq equals to 2r, hq equals to 2r. So from this equality we will conclude that dn also equals to 2r, dn also equals to 2r, so what is the size of AZ? According to the drawing, the size of line segment AZ is actually the size of DA minus ND. Again, AD minus ND equals to AZ. Okay, or AD or DA, it is the same, minus DN equals to AN. Okay, I'll repeat again. The size of line segment AN is actually AD, that is the side of the square ABCD, minus ND. That is the side of this, that is actually one of the sides of the square D edge and Q. Okay, so actually AN equals to AD equals to 8 units because of the fact that all the sides of a square are equal to each other, and one side equals to 8, so 8 units, so the other side will be also equal to 8 units, so AD equals to 8 units minus ND or DN equals to 2R. So in total we found out that NA equals to 8 minus 2R. So as I've already said, that all the angles, all four angles in a square are right angles. Therefore, angle DAB, this angle, equals to 90 degrees. Angle DAB equals to 90 degrees. Again, angle DAB is one of the square angles that equals to 90 degrees. But we know that angle DAB consists of four angles, so the sum of those four angles is equal to angle DAB. So 2 alpha plus 2 beta equals to angle DAB. Okay, so angle DAB equals to 2 alpha plus 2 beta. Therefore, 2 alpha plus 2 beta equals to 90 degrees, okay? 2 alpha plus 2 beta equals to 90 degrees. This will be equation number 1, that 2 alpha plus 2 beta equals to 90 degrees. So equation number 1 states that 2 alpha plus 2 beta equals 90 degrees. We will divide equation number 1 by 2, and we will get that alpha plus beta equals to 90 degrees over 2 is 45 degrees. So according to equation number 1, alpha plus beta equals to 45 degrees. If alpha plus beta equals to 45 degrees, then tangent alpha plus beta will be equal to tangent 45 degrees. Very simple. Tangent alpha plus beta equals to tangent 45 degrees according to equation number 1. But we know that tangent 45 degrees equals to 1, so we got equation number 1 that tangent alpha plus beta equals to 1. But we actually have trigonometric identity for the value of tangent alpha plus beta according to the following trigonometric identity. The value of tangent alpha plus beta is actually tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. Okay, so according to this trigonometric identity, we can substitute tangent alpha plus beta by this expression, because this expression equals to tangent alpha plus beta. So we will do it now. We will substitute tangent alpha plus beta by this expression that equals to tangent alpha plus beta, and we will get that instead of tangent alpha plus beta, we will write down that tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta equals to 1. Okay, so we actually substituted tangent alpha plus beta by this expression, and we got this expression. This is equation number 1. In the next step, we will find out the values of tangent alpha and tangent beta, and we will substitute tangent alpha and tangent beta in this equation number 1 by the values that we will find out for tangent alpha and tangent beta. Okay, so we will derive the values of tangent alpha and tangent beta from the drawing. So we will focus on the right triangle, triangle APM. So in the right triangle, triangle APM, tangent alpha equals to PM over AM. Again, tangent alpha equals to PM over AM. And we know that PM equals to R, and AM, according to what we have already found, AM equals to 8 minus R. So in total we got that tangent alpha equals to R over 8 minus R. Again, the value of tangent alpha equals to R over 8 minus R. In the same way, we will find out the value of tangent beta. We will focus on the right triangle AZQ. So in the right triangle AZQ, tangent beta equals to ZQ over ZA tangent beta equals to ZQ over ZA, but we know that ZQ equals to 2R, and we have already found out that ZA equals to 8 minus 2R. So in total we got that tangent beta equals to 2R over 8 minus 2R. So we found out that tangent beta equals to 2R over 8 minus 2R, and tangent alpha equals to R over 8 minus R. So we will substitute tangent alpha and tangent beta in equation number 1 by the values that we found here for tangent alpha and tangent beta. So we'll do it now. So according to equation number 1, we have tangent alpha, but we found out that tangent alpha equals to R over 8 minus R, so we write down R minus 8 minus R instead of tangent alpha in this equation number 1, plus tangent beta. We have already found out that tangent beta equals to 2R over 8 minus 2R, so we will write down 2R over 8 minus 2R instead of tangent beta, and we must divide it by 1 minus tangent alpha, that is R over 8 minus R, times tangent beta, that is 2R over 8 minus 2R. Okay, so all equals to 1. I repeat again, we substituted tangent alpha and tangent beta in equation number 1 by the values that we found here for tangent alpha and tangent beta, and we got this equality. Here we will take a common factor for these two expressions in the numerator, and we will also take a common factor for 1 in this expression in the denominator, and we will get that the common factor in the numerator will be 8 minus R times 8 minus 2R, and here we have R, so we must multiply R by 8 minus 2R in order to get R over 8 minus R. So this expression equals to this expression, plus 2R, we must multiply 2R by 8 minus R in order to get this expression. So actually this expression is equal to this expression, and all divided by 1 over this expression. So we'll substitute 1 by 8 minus R over 8 minus R, that is 1, and we will multiply it by 8 minus 2R over 8 minus 2R, that is also 1. So we write down this expression that is exactly equals to 1. 8 minus R over 8 minus 1 over 8 minus R equals to 1, and also 8 minus 2R over 8 minus 2R equals also to 1, and 1 times 1 is 1. 1 times 1 is still 1. So actually this expression is 1. So here, we have here 1 minus this expression, and we have the common factor here. So 2r times r is 2r squared, so it is minus 2r squared. So we actually have 8 minus r times 8 minus 2r in the denominator, and we have 8 minus r times 8 minus 2r in the numerator. So 8 minus r times 8 minus 2r will get cancelled because we have them both in the numerator and the denominator, so it will get cancelled. And what is left after we cancelled 8 minus r times 8 minus 2r is actually so I write it in a new page. What is left is actually here. I will open the brackets. R times 8 is 8r. R times minus 2r is minus 2r squared. Plus 2r times 8 is 16r. 2r times minus r is minus 2r squared. This is what is left in the numerator, and in the denominator we have 8 times 8 is 64. 8 times minus 2r is minus 16r. And minus r times 8 is minus 8r. And minus r times minus 2r is plus 2r squared. And we must not forget this expression, that is minus 2r squared equals to 1. So actually we open the bracket in this expression and we got this expression. Here we have 2r squared minus 2r squared is 0. So those two expressions in total equals to 0, so they will cancel. And what we have here is 8r plus 16r is 24r. Minus 2r squared is minus 4r squared. And what we have in the denominator, we have 64 minus 16r minus 8r is minus 24r. All equals to 1. So here we will cross multiply this equation number 1, and we will get that 24r minus 4r squared equals to 64 minus 24r. So here we will subtract from this equality for equation number 1 24r, and we will get that minus 4r squared equals to minus 48r plus 64. Here we will add to this equation number 1 4r squared, and we will get that 4r squared minus 48r plus 64 equals to 0. So we have here a quadratic equation. We will divide this quadratic equation by 4, and we will get that r squared minus 12r, 84 over 4, 48 over 4 is 12, so it is minus 12r, plus 64 over 4 is 16. So we actually got this quadratic equation, and actually the general formula for a quadratic equation is ax squared plus bx plus c equals to 0, when a, b, and c in this general quadratic equation are the coefficients of this quadratic equation, and x is the variable that we are looking for, and we will find out the value of x according to a special formula for x. The following special formula, that is x equals to minus b plus minus root of b squared minus 4 times a times c over 2a. Okay, so we will use this formula in order to find out the value of x. In our specific quadratic equation, the variable is r, so x equals to r in our specific quadratic equation, and the coefficients a, b, and c are actually a equals to 1, b equals to minus 12, and c equals to 16. So we will put this data inside the formula for x in order to find out the value or the values of r, that is the radius of the small circle. So x equals to r, so r equals to minus b, b equals to minus 12, so minus 12 is 12, plus minus root of b squared is minus 12 squared, minus 12 squared is 144, minus 4 times ac, minus 4 times a is 1, so minus 4 times 1 is, minus 4 times 1 is 4, minus 4 times 1 is minus 4, and minus 4 times 16 is minus 64. All divided by 2 times a is 1, so 2 times 1 is 2. So we got that the radius of the small circle equals to 12 plus minus 144 minus 64 is 80. So what is left inside the root is 80 over 2. So in total we got that the radius of the small circle equals to this expression, but we know that 80 equals to 4 times 20, so I'll write it down. R equals to 12 plus minus root of 4 times 20, that is 80, over 2, so R equals to 12 plus minus, the root of 4 is 2, inside the root we have only 20, over 2. Okay, so R equals to 12 over 2 is 6, 2 over 2 is 1, and 20 equals to 4 times 5. Instead of 20 we will write down 4 times 5. So actually we got that R equals to 6 plus minus, the root of 4 is 2, and inside the root we have only 5 left. So we have the solution that R equals to 6 plus minus 2 times root 5, so R either equals to 6 plus 2 times root 5, or r also can be equal to 6 minus 2 times root 5. So we have two possibilities for r, or two roots for r. Okay, but we know that AB equals to 8 units, and all the sides of a square are equal to each other, and those two circles are located inside the square, and especially the small circle is located inside the square. Therefore, the radius of the small square must be less than 8 units because of the fact that the small square is located inside, because of the fact that the small circle is located inside this square. Therefore, the radius of this small circle must be less than 8 units because of the fact that it is located inside this square. And the size of one side of the square is 8 units, so the radius must be less than 8 units. And here we have r that equals to 6 plus 2 times root 5. 6 plus 2 times root 5 is greater than 8 units. And we must have that the radius of the circle, as I already told you, because of the fact that it is located inside this square, the radius must be less than 8 units. R is less than 8 units, and we have here R that is greater than 8 units. Therefore, this answer is not correct. It is not possible for our case, and the only answer that is left for the radius of the small circle is that r equals to 6 minus 2 times root 5, and that is the only answer that is left, that the radius of the small circle equals to 6 minus 2 times root 5. That is actually about, in terms of numbers, it is about 1.53 units. So we found out that the radius of this small circle is either equals to 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 1.53 units. Okay, that is the answer to the question. So in the next step we will summarize the lecture. Actually, we wanted to find out the radius of this small circle, and in order to find the radius of this small circle, I presented to you two rules. The first rule that I presented to you is that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if you have this circle and tangent AB that is tangent to this circle at point M, and you have this radius that is drawn to the point of tangency, that is to say point M. Point M is the point of tangency. As you can see from the drawing, this radius is drawn to the point of tangency that is point M. Therefore, according to rule number 1, this tangent AB is perpendicular to this radius, that is to say this angle is 90 degrees and this angle is 90 degrees. So whenever you have a radius that is drawn to the point of tangency, like in this drawing, then the tangent will be perpendicular to that radius. That is to say this angle is 90 degrees and this angle is 90 degrees. So this is rule number 1. And I also presented to you rule number 2. According to rule number 2, if from one external point two tangents are drawn to a circle, then they have equal lengths. So what is the meaning of rule number 2? If we have this circle and external point, again point P is external point in relation to this circle because it is not located inside this circle, and it is also not located on the circle, but it is located outside the circle. Therefore it is defined as external point in relation to this circle. So if from the external point P you draw two tangents to this circle or to any circle, then the lengths of those two tangents will be equal to each other. That is to say, PA will be equal to PB. Okay, again, if you from external point of a circle you draw two tangents to the circle, then the lengths of those two tangents will be equal to each other. That is to say, PA equals to PB. This is rule number 2. Then we actually defined the center of the small circle as point P, and the circle and the center of the big circle as point Q. We join together points A and P by a straight line. We join together points P and M by a straight line. Actually, we have this radius that is drawn to the point of tangency, that is to say, it is drawn to point M. Therefore, the tangent AB will be perpendicular to this radius, that is to say, this angle equals to 90 degrees, and this angle is also equal to 90 degrees. And we also join together points P and E by a straight line. And again, PE is the radius of the small circle because of the fact that it starts from the center of the circle and ends at point E, that is a point on the small circle itself. Therefore, PE is the radius of the small circle, and we have this radius that is drawn to the point of tangency, that is to say, it is drawn to point E. Therefore, the tangent AF is perpendicular to this radius, that is to say, this angle is 90 degrees and this angle is 90 degrees. Then we actually proved that those two right triangles can go into each other. Why? Because we have AM that equals to AE according to rule number 2. What is rule number 2? If from the external point A we have two tangents to this small circle, tangent AM and tangent AE, then the lengths of those two tangents are equal to each other. That is to say, AM equals to AE according to rule number 2. And we also know that PEM equals to PE equals to the radius of this circle. And also we have PA that is a common side, so PA equals to PA as a common side that belongs to both triangles. Therefore, we actually proved that all three sides of the right triangle AMP are corresponding equal to all the three sides of the right triangle AEP. Therefore, we proved that those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we concluded that those two angles are equal to each other. And if one angle equals to alpha, then the other angle will be also equal to alpha. So actually we got that angle MAP equals to angle PAE, and it equals to alpha according to our definition. And we then connected together points A and Q by a straight line. Then we connected together points Q and L by a straight line. QL is the radius of the big circle because of the fact that it starts from the center of the circle and ends at point M, that is a point on the circle itself, on the big circle itself. Therefore, QL is the radius of the big circle. And we have this radius of the big circle, QL, that is drawn to the point of tangency, that is to say, to point L. Therefore, according to rule number 1, the tangent AF is perpendicular to this radius, that is to say, this angle is 90 degrees and this angle is also equal to 90 degrees. And the same thing is true here. Qn is the radius of this circle for the same reason. It starts from the center of the circle and ends at point N, that is a point on the circle itself. Therefore, Qn is the radius of this circle, and this radius of this circle is drawn to the point of tangency, that is to say to point N. And therefore, according to rule number 1, the tangent AD is perpendicular to this radius. That is to say, this angle is 90 degrees and this angle is 90 degrees. And then we proved that those two right angles can go into each other. First of all, we know that AL equals to AN. AL equals to AN because of the fact that point A is an external point in relation to the big circle, and from the external point A we drew two tangents to the big circle, tangent AL and tangent AN. And according to rule number 2, the lengths of two tangents from an external point of a circle are equal to each other, that is to say AL equals to AN according to rule number 2. And we also know that QL equals to QN equals to the radius of this big circle, and AQ is a common side, it belongs to both right angles, so QA equals to QA, it's a common side. So we proved that all the sides of the triangle AQL are corresponding equal to all the sides of triangle NQL. According to side-side rule, those two triangles can go into each other. And from the fact that those two triangles can go into each other, we will conclude that those two angles are equal to each other, according to the rule that corresponding angles in congruent triangles are equal to each other. And if one angle equals to beta, then the other angle will be also equal to beta because of the fact that those two angles are equal to each other. So we found out that angle LAQ equals to angle ZAQ equals to beta according to our definition. Okay? Then we focused on this quadrilateral PSMB. We know that this is one of the square's angle, and all the angles of the squares are right angles, so this angle is a right angle, this angle also a right angle, as we have already proved, and this angle, it is also a right angle because of the fact that the radius PS is drawn to the point of tangency, that is to say to point S. Therefore, the tangent BC will be perpendicular to this radius, that is to say this angle is 90 degrees and this angle is 90 degrees. So in quadrilateral PSMB we have three right angles, and the sum of three right angles is 270 degrees. And we have the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral PSMB, we know that the sum of four angles is equal to 360 degrees. That is to say, the sum of three angles, that is 270 degrees, plus the size of the fourth angle must be equal to 360 degrees according to the rule that is stated. So here we subtracted 270 degrees from this equality, and we got that the size of angle Z is 90 degrees. Therefore, this angle is a right angle. So we have here quadrilateral PSMB that has four right angles. And any quadrilateral that has four right angles, it must be at least rectangle. So quadrilateral PSMB, it must be at least a rectangle, if not a square. And we have the rule that the opposite sides of a rectangle are equal to each other. That is to say, PS equals to MB. PS equals to MB, but we know that PS equals to R. PS equals to R. So from this equality we will get that MB also equals to R. So MB here equals to R. And according to the rule that the opposite sides of a rectangle are equal to each other, PM also equals to SB. And from the fact that PM equals to SB, but we also know that PM is the radius of the small circle, that is to say PM equals to R. So from this equality we can derive that SB also equals to R. SB also equals to R. So actually, because of the fact that all the sides of quadrilateral PSMP are equal to each other and it has 4 right angles, it is not a rectangle but it is a square, okay? And we repeated on the same process on this quadrilateral DHQN. Actually, we connected together points Q and H by a straight line. Q edge is the radius of the big circle, it equals to 2R, and this radius is drawn to the point of tangency, that is to say to point H. Therefore, the tangent DC is perpendicular to this radius, that is to say this angle is 90 degrees and this angle is also 90 degrees. And we know that all the angles in a square, inside the square, are right angles, so this angle that is one of the square's angles are also right angles. Right angle is equal to 90 degrees, and also Rn is the radius of the big circle, and this radius is drawn to the point of tangency, that is to say to point N, and therefore the tangent AD or DA is perpendicular to this radius, that is to say this angle is 90 degrees and this angle is also 90 degrees. So if we focus on quadrilateral DNQ, we can see that quadrilateral DHNQ has 3 right angles, 1, 2, 3. And we have the rule that the sum of the angles in any quadrilateral equals to 360 degrees. So those 3 angles, that the sum of them is 270 degrees, plus the size of the fourth angle that we defined as angle Z must be equal to 360 degrees according to the rule that I mentioned 1 second ago. So 270 degrees, that is the sum of 3 angles of quadrilateral DHNQ plus the size of the fourth angle must be equal to 360 degrees. We subtracted 270 degrees from this equality and we got that the size of angle Z is 90 degrees, so this angle is a right angle. So we have quadrilateral DHNQ that has 4 right angles. Any quadrilateral that has 4 right angles must be at least rectangle. So okay, so quadrilateral DHZQ must be at least a rectangle, and we know that the opposite sides of a rectangle are equal to each other, that is to say DH equals to NZ, DH equals to NQ, DH equals to NQ, okay, DH equals to NQ. But we know that NQ equals to the radius of the circle, that is 2R. NQ equals to 2R. So from this equality we will derive that DH also equals to 2R. DH also equals to 2R. And we also know that the opposite sides in rectangle DH and Q, those two opposite sides HQ equals to DN, according to the rule that the opposite sides of rectangle are equal to each other. So DN equals to HQ. But we know that HQ or QH equals to 2R. HQ equals to 2R. So from this equality we will derive that DN also equals to 2R. DN also equals to 2R. So actually we have quadrilateral with 4 right angles, and all the sides of this quadrilateral DL and Q are equal to each other, therefore it is a square. Okay? Quadrilateral DH and Q is a square, and we have this angle BAD is a right angle because of the fact that all the angles inside the square are right angles, so this angle that is inside square ABCD is a right angle that equals to 90 degrees. So actually angle DAB equals to 90 degrees, and the angle DAB consists of 4 angles, alpha, alpha, beta, and beta. So 2 alpha plus 2 beta equals to the size of angle DAB, that is actually 90 degrees. Okay, angle DAB equals to 2 alpha plus 2 beta, but for one side, but for the other side, angle DAB also equals to 90 degrees. So we can derive from it that that 2 alpha plus 2 beta equals to 90 degrees, because this angle is a right angle. And so we will divide equation number 1 by 2, and we will get that alpha plus beta equals to 90 degrees over 2 is 45 degrees. We got in equation number 1 that alpha plus beta equals to 45 degrees. If alpha plus beta equals to 45 degrees, then tangent alpha plus beta will be equal to tangent 45 degrees. And tangent 45 degrees is 1. And so we got in equation number 1 that tangent alpha plus beta equals to 1. And we have trigonometric identity for the value of tangent alpha plus beta according to this trigonometric identity in the red color. Tangent alpha equals to this expression, so we can substitute tangent alpha plus beta in equation number 1 by this expression. So we did it here. We substituted tangent alpha plus beta by this expression, and we got this equation number 1. Then we calculated the values of tangent alpha plus beta in order to put them inside this equation number 1. What is the value if we focus on the right triangle APM, this right triangle, according to the drawing, tangent alpha equals to PM over AM. Tangent alpha equals to PM over AM, or MA or AM, it is the same. PM equals to R, and AM equals to 8 minus R. We have already found that AM equals to 8 minus R, so actually tangent alpha equals to R over 8 minus R. So in total we got that tangent alpha equals to R over 8 minus R, and then we calculated the value of tangent beta. We focused on the right triangle AZQ. In the right triangle AZQ, tangent beta equals to ZQ over, in the right triangle ANQ, tangent beta equals to NQ over AN. Tangent beta equals to, okay, so this letter as N and as Z, so actually, but if you look from this side it is N, but okay, so let's see it as angle Z. So tangent as the letter Z, so tangent beta equals to ZQ over ZA. Tangent beta equals to ZQ over ZA, but ZQ equals to 2R and ZA equals to 8 minus R. So in total we got that tangent beta equals to ZQ, that is 2R, over ZA, that is 8 minus R. So we found out the values of tangents alpha and tangents beta, and then we substituted tangents alpha and tangents beta in equation number 1 by the values that we found out here, and we got this equation after we substituted tangents alpha and tangents beta by the values that we found out for tangents alpha and tangents beta. We solved this equation. It is actually a quadratic equation, and we got to 2 answers. We have 2 answers for the quadratic equation that we got. The first answer is actually R equals to R, the radius of the small circle, equals to 6 plus 2 times root 5, and the second answer is that the radius of the small circle equals to 6 minus 2 times root 5. But we know that the size of one side of square ABCD equals to 8 units. And the two circles are located inside the square. That the sides of the square, one side equals to 8 units. And because of the fact that one side of this square equals to 8 units, the radius of the small circle must be less than 8 units because of the fact that it is located inside the square. And one side of square is 8 units, so the radius must be less than 8 units in order to locate the small circle inside this square, as we can see from the drawing. So the answer that the radius of the small circle equals to 6 plus 2 times root 5, that is bigger than 8 units, is not correct because of the fact that the small circle is located inside the square. So the radius must be less than 8 units. So the only answer that is left is that the radius of the small circle equals to 6 minus 2 times root 5 units. And in terms of numbers, the radius of the small circle equals to 1.53 units. I will repeat again. The radius of this small circle equals to either to 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 1.53 units. Okay, thank you very much.